Welcome to my webinar on Western Australian microbialites. My name is Heidi Allen and I am a paleontologist with the Geological Survey of Western Australia. What I hope to do in this webinar is give you some of the highlights of a 3.5 billion year fossil record of microbialites in our state. There are many definitions of what a microbialite is, but for the purpose of my talk I will be referring to structures that fall under this definition of Byrne and Moore. This definition states that microbialites are organosedimentary deposits that have accreted as a result of a benthic microbial community. These structures can be built by either the microbial community trapping and binding detrital sediment or by direct mineral precipitation, but commonly both processes will be occurring. This simplified graphic shows the means by which a microbialite forms. We have a community of microbes that congregate, and a process of either trapping and binding of sediment will occur or direct precipitation in place will begin. Often, as the structure accretes, the microbes will keep pace by migrating to the outer or living edge, and the process continues until a resulting structure, a microbialite, is formed. What is left behind is the structure that was accreted by the microbial community. Here we have an example of a fossil stromatolite from the Tumbiana Formation. It is not very common for microfossils to be preserved within the microbialite. Generally speaking, the microbes are long gone, and what remains is the structure they have left behind. I love this example from the Tumbiana Formation as it beautifully shows the microbialite within its sedimentary context. Stromatolitic laminations are relatively flat at the base and begin budding branches once it reaches a critical height. Microbialites can be divided into subsets based on their overall morphology. Stromatolites, the first and probably most common described subset, are microbial buildups that have a laminated or layered structure. Thrombolites, the second subset, have an internal clotted structure at the macro scale. Dendrolites have a shrub-like appearance, branching in a dendritic fashion as their name suggests. Localities might seem a bit odd as a subset when by definition they are structureless, but they can be easily recognised in the field by their microbial bed forms, their shape and the context of their growth. Microbially induced sedimentary structures, or MISS, are quite different in their appearance to the first four subsets, and generally found in different stratigraphic settings. Whilst the first four subsets are usually found in carbonate-dominated regimes, MISS are features found on bedding planes, commonly in clastic settings. But when we adopt this broad definition of microbialites as deposits that form as a result of a benthic microbial community, they do fit here as a fifth subset. So now you know what a microbialite is, you might be wondering why a paleontologist from the Geological Survey of Western Australia is giving a webinar on them. There is a very good reason for this, and that is that they are the most commonly found macrofossil in our state. Currently there are more than 2,000 documented microbialite localities in WA, and this number is only increasing with each new project we undertake. Also, microbialites have the longest fossil record of any life on Earth. But exactly how old is that record? The oldest known widely accepted microbialites are found here in the Pilbara region of WA. Here we have an example of a stromatolite that is almost 3.5 billion years old from the Dresser Formation in the Pilbara area of WA. This formation has undergone extensive research in recent years thanks to it being an excellent analogue for the search for life on Mars. Some exciting research undertaken by Tara Jokic from the Australian Centre of Astrobiology documents the occurrence of these early stromatolites with geyserite, a form of opaline silica found around hot springs and geysers. Tara's research, undertaken with Martin van Kranendonk, a former GSWA mapping geologist, suggests that life may have first arisen in this setting. For our next stop, we move to the slightly younger Strelley Pool Formation, also in the Pilbara region of WA. Sites here and those of the Dresser Formation are protected geoheritage reserves administered by the Geological Survey of Western Australia. Access to these sites requires an application to be made through our department. The reason these sites are protected is because, as well as being some of the oldest evidence of life on our planet, they are also some of the best documented. This site is known as the Trendle Reserve, as it was first discovered by former GSWA Director Alec Trendle. A number of different stromatolite forms occur at this locality. There is a small conical stromatolite known as the egg carton stromatolite. This piece pictured below in the field was collected by GSWA geologists and is now the centrepiece of the stromatolite display in the Origins Gallery at Boulevardiep, the new WA Museum. Here is another stromatolite form common at the same site, called Mickey Mouse ears for obvious reasons. Moving forward in time, we have many more microbialite sites. I have skipped over quite a few to highlight the Tumbiana Formation stromatolite, Outsheringa Narrana. This form was originally described by Malcolm Walter in 1972. When described, it was the oldest known Australian stromatolite at 2.7 billion years old. It has gone on to become one of Australia's most iconic stromatolites, gracing the cover of Outsheringa, an Australasian Journal of Paleontology, since 1975. These stromatolites, as well as being strikingly beautiful, also capture the imagination as they are an example of life living on the edge. Occurring within tufaceous deposits, these stromatolites were thriving during a time of active volcanism. Our next stop in time exploring WA microbialites brings us to 2.4 billion years ago, a time that marks what is known in Earth's history as the Great Oxidation Event. This event marks the point in time when the Earth's atmosphere and shallow oceans experienced a rapid rise in oxygen. Microbialites at this point in time were photosynthesizing, harvesting energy from the sun, and oxygen was being released as a waste product. These tiny but mighty microbes were essentially the trees of the Proterozoic. On the top right of this slide there is a graph which shows this stepped accumulation of oxygen in the Earth's atmosphere. The bottom axis is time in billions of years, beginning on the left at 3.8 billion years and ending on the right at the present day. The vertical axis indicates the amount of oxygen present in the Earth's atmosphere. You can see the rise in oxygen indicated at the arrow begins at 2.4 billion years ago. At the same time as this rapid accumulation of oxygen in the Earth's atmosphere was deposition of the Toohey Creek group. This is a project I am actively working on with Dave Martin, a senior geologist here at GSWA. Many of these microbialites forming coeval with the Great Oxidation Event are undescribed, but have proven to be very good temporal markers for regional mapping. Here is a profile view of a linked conical stromatolite. Higher in the section, there are very large thrombolytic bioherms. In this photo, in the foreground, you can see one of these thrombolite bioherms. In the background of this photo, the buff-coloured unit is onlapping bedded carbonate. Here is a different view of the same bioherms. The microbialite build-up is the grey weathering carbonate, with the bedded carbonate being more orange in colour. Here is Dave Martin for scale with a bioherm in the Caspert formation of the Toohey Creek group. Some of the bioherms grew to an enormous size. In this photo you can see several bioherms in an exhumed topography, as the carbonate mud between the bioherms is more easily eroded. I could talk about these microbialites all week, but we must move along in time. After the Great Oxidation Event, the Earth's biosphere responded. In the interval following this event, we get the rise of more complex life forms. We get the beginnings of megascopic eukaryotic algae, like this Grypania here, over a centimetre in size, as well as examples of microscopic life becoming far more complex in their cell structure. During this exciting time in Earth's history, life in WA persisted on, and we have several excellent microbialite localities in the preceding interval. In this slide, I have included exposures of the Duck Creek dolomite in another of the state's geoheritage sites, the Duck Creek Gorge. Here, alternating cycles of the two stromatolite forms Pilbaria and Asperia are expressed as this banded section. This site has been extensively studied for both its amazing microbialites, but also its diverse and abundant microfossils that are preserved in early diagenetic chert nodules in some parts of the section. Fast-tracking through the Proterozoic, bypassing many more hundreds of microbialite sites, we skip through to the Neoproterozoic. This was a time when Earth enters another interval of change as oxygen was once again rapidly increasing in the Earth's atmosphere. At this time, the Centralian superbasin was being deposited not only across WA, but right across Central Australia. Units of the Centralian superbasin span the Neoproterozoic and includes the record of at least 2 global glaciations. The Neoproterozoic era is well known globally for its abundant and diverse microbialites. Peter Haynes, a GSWA Basins custodian, and I have been working together on the WA constituents of the Centralian superbasin for more than a decade now, revising stratigraphy in the Amadeus, Officer and Maraba basins. Here on this slide are a few examples of microbialites we have described from the Amadeus basin. For this project, we have been using microbialites for regional correlation. When systematically described, microbialites make reliable temporal markers that can be used for regional mapping of units. There are 5 main assemblages that can be differentiated on their stromatolite forms and stratigraphic occurrences, but infilling of this scheme is still ongoing. Moving ahead in time, past the stromatolitic Tonian and Cryogenian periods, we again find ourselves at a very significant time for the Earth's biosphere. This is the time that we see the first record of complex multicellular organisms. A beautiful and bizarre world of marine organisms. Here are some South Australian examples of the Ediacaran biota. The iconic Dickinsonia at the top, along with a range of complex soft-bodied organisms that made for a very lively seafloor. Unfortunately though, just as complex life starts to take off, we see an end to when microbialites ruled on Earth. With the onset of bioturbation and the rise of grazing organisms, microbialites enter a period of decline. Sometimes referred to as the Cambrian agronomic revolution, this is a time when the Earth undergoes massive amounts of change. Life moves from mat grounds to a state where the animals are living in, on and above the sediment-water interface. It is a very exciting time in our fossil history where you get fossils like trilobites seen here, but unfortunately for microbialites, it was the beginning of a time when they were largely outcompeted for resources and substrate. But it is not all doom and gloom. There are still some Phanerozoic microbialite sites, and interestingly, the majority of these documented sites are linked to a time in Earth's history when the biosphere was in crisis. There are 5 known mass extinctions of the Phanerozoic, and it has been well documented that following mass extinction events, microbialites temporarily move back in again and take up space in ecological niches that prior to extinction events they were outcompeted in. One such site documented from here in WA is located within the Blue Hills Geoheritage Site. This stromatolite from our collection is now on display in the new WA Museum Bullabardip. This site is unfortunately poorly constrained in age, but these microbialites have previously been documented as a disaster fauna associated with the largest of all the mass extinctions, the Permian-Triassic extinction event. Moving forward ahead in time again, no talk on WA would be complete without featuring one of WA's most iconic microbialite sites, Shark Bay. As well as over 2,000 localities of fossil microbialites in our state, we also have a wealth of modern analogues. In fact, this is something that makes our state globally unique. In relatively close proximity, you can see both fossil and living examples of microbialites. Located on our Midwest coast is the area of Shark Bay, a series of embayments. The Fiore Sill, an embankment stabilised by seagrass, encloses an area called Hamlin Pool. This resulting enclosure of Hamlin Pool creates a hypersaline environment which is very hostile for the majority of marine organisms, but not stromatolites. Living microbialites are found along the 135-kilometre stretch of coastline contained within Hamlin Pool. This site is located in the southeast corner of the Hamlin Pool and is called Flagpole Landing. It is one of the easiest sites to access and has a boardwalk above the structures to protect them. This picture was taken at a very low tide, but the structures you can see in the photo here are in the intertidal zone and are submerged at different times. At the site there is a zonation of the features that you can see. Here is the boardwalk. It zigzags across the site so you can enjoy a good view of the microbial mats as you enter. There are a number of different microbial mats within the intertidal zone. These ones are photographed near the high tide mark. The mat morphology changes depending on the dominant microbes within the assemblages. Here in the photo you can see two mat forms. The darker one is a pustular mat, with the lighter one being finer in texture that is more tufted. As you move further out into the intertidal zone, you get these taller columnar stromatolites, with many of them coalescing here to form complexes. And what is common to note is their elongation in a direction that is parallel to water movement. Although this elongation can be observed as perpendicular to the shoreline in some places, in others it can be offset by as much as 30 degrees, and the elongation is more controlled by the prevailing wind direction. Here you can see a slice through one of the columns from our paleontology collection. Usually described as stromatolites, they are layered structures, but there are common overgrowths of what would be better described as strombolites. What is known about to a lesser extent is that living microbialites also occur in a series of inland lakes here in WA. Here are some thrombolites from Lake Clifton that are located just over an hour's drive south of Perth. Sadly, this slide brings to a close our 3.5 billion year journey looking at some of my favourite microbialite localities from Western Australia. But I can appreciate some of you may be left wanting more information. We have many excellent resources you can track down to expand on this webinar. Our recently published Bulletin 147 has a wealth of information about the description of microbialites, as does GSWA Bulletin 146 on Shark Bay. Some other reading you may enjoy are records on Lakes Thetis, or a management plan for the State Geoheritage Reserves that cover many of the Pilbara early life sites, as well as our Discovery Trails to Early Earth book. All of these publications are free to download from our webpage eBookshop. Alternatively, if there is any more information we can help you with, feel free to drop us a line at paleontology@dmers.wa.gov.au.